because there is an axial load, okay, of 2,500 pounds. Okay, so we cannot use this formula. Okay, so this formula over here is invalid. So you have to be careful. Okay, right? You have to be careful. So we're going to analyze the stresses on this beam. Okay, so let's see how the structure is loaded first. I think the more important thing is to see how the structure is loaded first. Okay, so we draw our transformation like before. Okay, this is just another add-on in our analysis. Okay, it's compound loading basically. So we draw, this is our X, this is our Y, and over here that is our Z. Okay, so if we look at our loads, I'm going to copy this. Okay. We know that we have a PX is equal to minus 2,500 pounds. Okay. Then we have a torque in the X, right? Torque in the X of 2,300 pound-feet. Now feet we have to change to inches, or 2,300 multiplied by 12. Okay, so this is equal to 2,300 is 27600 pound inch. Okay, and then we have a moment in Z. So the moment in Z, 1,500 pound feet, or 1,500 multiplied by 12 is equal to 18,000 pound inch. And then we are given that our normal stress in yield is equal to 100 times 10 to the power 3 psi. Our shear stress in yield is also equal to 50 times 10 to the power 3. Yes. Okay, we are given these two values. So we are asked to identify what is the minimum diameter. Okay, using find minimum diameter using Tresca criteria. Now we know that Tresca criteria has two forms. Okay, what do I mean by that? So it has two forms because are we going to apply tau max is equal to stress max divided by 2, or are we going to apply tau max is equal to stress max minus by stress mean, right, divided by 2. Okay, so this is all dependent on what? on our structure analysis. Okay, so you remember we drew this, right? We drew this. The first one sorry. So we drew this, and when we sketch this out, we did mention that for this case, right, one of the principal stress, right, is equal to 0, right, for the one on the left hand side is where stress, or one of the principal stress, or one of the principal stress is equal to 0. If not, right, then we have to use the other formula. Okay, we have to use this formula where the mole circle looks like this. Okay, so for this case, hold on, it looks a bit messy over here. I think I can get rid of this. So which formula to use, right? Which formula to use? It depends on your mole circle. It depends on your mole circle, right? Is our stress state where one of the principal stress is equal to 0? Or is it when none of the principal stresses are equal to 0? Okay, so either this formula to use or this formula to use, right? It depends on the is one of the principal stresses is equal to 0. Okay? So for now, we don't know yet. Okay, we don't know yet. So the first thing we're going to do now is we are going to look at the front end, okay, of the shaft. Okay, so by looking at the transformation, okay, we are going to view the shaft on the YZ plane. Okay, we're going to view the shaft. So the next thing we're going to do, so before we know whether is it sigma max is equal to or tau max equal to sigma max divided by 2, or tau max is equal to stress max minus stress mean divided by 2. Okay, we don't know yet. Okay, so we have to find. Okay, we have to locate the position or the failure position. So that's where we now do failure analysis. Okay, locate the failure position. Okay, so we are going to look at the YZ plane. I'm going to sketch the YZ plane. Okay, so I'm going to draw the center line. And I'm going to have elements. Okay, we're going to have elements. So I'm going to call this element A, element B. Hey, come on. Element B, element C, and over here, element D. Okay. So we're going to draw a table. So why I put the elements there? Because I believe, or we believe, that one of the elements are not loaded in the same stress state. Okay. So we're going to look at element A, element B, element C, element D. Okay, so we're going to look at the stress state. So the first stress that we're going to look at, okay, is due to the axial load. So stress X is equal to Px over A, right? So we know that Px, right, given over here, is equal to 2,500. Okay. So Px is equal to 2,500 pound inch. Now, with the axial load, right, all of them are going to see negative Px over A. So due to axial loading, the stresses induced on element A, B, C, D are all the same. Okay, element A, B, C, D. And then the next one we're going to look at is the one due to bending moment. Okay, so M. So we're going to look at moment about the z-axis. Okay, so if you look using the right hand rule, right, the moment vector is acting in this direction, mz. So we realize that mz is in this direction. Mz. Okay. So this is compression and this is tensile. And then we are going to calculate normal stress. X is equal to mz over izz multiplied by y, where we know that mz is equal to, we calculated mz, and it is 18,000 pound inch. Now, if we look at element A, it's going to be positive mx multiply y over izz, right? Point B is at the centroid is equal to 0. Sorry, element B. Element C is equal to minus mx, oh sorry, mz. Okay, one is positive mz. The other one is minus mz multiplied by y over izz. And then element D is equal to 0. And then the last one, which is due to the torque, right? The last one is due to the torque. So the shear is equal to Tx over J multiplied by R, where Tx is equal to, we calculated Tx is equal to 27600. So all of them have Tx R over J is a constant. All of them, because all of them are at the radius of the shaft. So now we have to decide the element that's under the most critical loading, and it is element C. Why element C? Because both the normal stresses induced by axial loading and bending moment are negative. Okay, it's not element A because the axial loading is compression. The bending moment is inducing tensile stress. Okay, so with this, we know that failure will occur at element C, right? Okay, so now we are going to sketch the element. Okay, but before we sketch an element, let's take a 5 minutes break and we come back. 5 minutes. We come back at 8:07. Okay.